So day 2 of our function review, we are going to cover function representation as well as functions versus non-functions and linear versus non-linear. Start with function representation. It can take form of 4 different forms. One, a graph, where we have our plotted points. They could be lines, curves, just a series of dots. They could be tables, our t-charts, inputs and outputs. They can be an equation, something as simple as f of x equals 3, to something complicated like 3x squared minus 2x plus 5. And the last way, it can be described with words that relate independent variables and dependent variables with the information given. So let's say we're given this graph and we need to convert it into the other 3 forms. So I know this is going to be the equation, our table, and our words down here. We can go about this in any order that we want. The table over here, we're going to include 3 points. This is pretty decent. 3 points, 4 points. So to do that, all we have to do is find any coordinate points over here that we want. Now we typically want to use whole numbers. For instance, I see a perfect point there, 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 here's another, here's another, here's another, here's another, here's another, here's another. We can use any of these points, but this line is actually a collection of an infinite number of points. So if we wanted to be super crazy, we could even pick that point. You know what? We could pick this point. We could pick that point. We could pick this point. Any coordinate points that happen on the line are potential answers. So let's say we take this point right here. We're going to be crazy. We're going to take this yellow point right here, and we're going to take that point. So this first one, the x-coordinate is 1. The y-coordinate is 0. We have ourselves points. This yellow point right here, come down to the x-axis. That is 1, 2, 3.5. We come over here, we get 1, 2, 3, 4, 5. And this last point is at 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. So the last point is at 5, 8. This table can consist of as many points, but since it's linear, it needs 2, because it's linear, at the very least. Our equation, now we could build the equation right from the table, or we could grab the information right from the graph. We're going to want slope, and we're going to want y-intercept. So I'm going to go through, I'm going to erase these points because we don't need all those. We're going to need one very special point in particular. That's this one. And then we're going to need some other point, doesn't matter which one. So we're going to take this next point right there. The smiley face is our y-intercept. It's at 0, -2. So we know in our equation, which we're going to build an mx plus b, is going to have a -2 on the end. Our slope, rise over run, from the smiley face to the target, up to over 1. So we have 2 over 1x minus 2. There's the equation of our line. The last thing for our word problems is we have to relate these 2 points together in some sort of story problem. IV and DV, we can make them up whatever we want. We're just going to keep it simple. Let's do time, and let's do feet. In our brief story, we're going to have to relate why we start at -2. So let's say we start, or we don't want to include negative in the story here. We want to include it in different ways. We start 2 feet behind. That illustrates the 2, and the behind part tells us negative. We now have to relate our ratio, this 2 over 1. Our ratio of 2 over 1 is dv feet over time. So we have to talk about 2 every 1. So in this case, we gain 2 feet every 1, and then the time probably should say in some sort of every 1 minute. Just like that, we've written a word problem that illustrates this story. We start 2 feet behind, and we gain 2 feet every 1 second. Say we start with the word problem in the beginning. IV is minutes, DV are chips left, so I guess I'm eating some food. So we have 13 chips on our plate, and we eat 3 chips every 2 minutes. Alright, so what's our start B? We start with 13 chips, and then what's happening is this 3 chips every 2 minutes, and since we're eating those chips, we're losing 3 chips every 2 minutes. Now that we have our information, we could go right to the equation if we wanted. We probably could get the graph. The table's probably a little bit tougher, so let's go one of these. I choose the equation. So f of x, again, we're going to have an mx plus b. Well, the motion here, 3 chips every 2 minutes. And we start with 13, and we have our equation. We could use the equation and just plug in random numbers, so we could plug in 0, we could plug in 1, we could plug in 2, we could plug in 3, so we have f of 0 equals negative 3 halves times 0 plus 13. And we could go through all of this work for the points that we picked. But an easier way is actually to take this and go to the graph next. This way you know how to graph our lines. Start up 13, down 3, 1, 2, 3, over 2, 1, 2, 3, over 2, 1, 2, 3, over 2, 1, 2, 3, over 2. Oh, that was only 2. Whoops. 1, 2, 3, over 2. And then we connect it with our line. And now that we have some points plotted, we can grab some of these points, let's say these 3 right here, and transfer them into the table. For instance, 2, 10, this first point. 4, 7. And then 6, 4. Now we went from words to the equation, to the graph, to the table. We can go in any order that we so choose. Say we have the equation. From the equation, we could go in any of these 3 directions that we want. I find it easiest to get the graph. It is backwards, so we could reorganize this as 2/3 x plus 6 to help us graph it a little bit better. It's the exact same. Notice that it's a positive 6 in both cases, and it's still a negative 2/3 in both cases. So we start up 6. 1, 2, 3, 4, 5, 6. Down 2, right 3. 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 Just gonna try to freehand this line. Not bad if I say so myself. Now that we have some points, we could easily copy those points into the table. For instance, we could take these 3 points. The first one's at 3, 4. This next one's at 1, 2, 3, 4, 5, 6, 2. This last point's at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, negative 2. Last but not least is to come up with the words. So I need some variables for IV and DV. They can be anything that we want. You can keep it simple like time and distance. I used chips on the last problem. On this one, I'm going to say same thing. Time in minutes. DV, let's say money. In our word problem, we have to incorporate our starting value. Why did I start at 6? Or what did I start with, I should say. This number here is always related to our DV. So we start with $6. Now this is more of a personal thing. The dollar sign goes on the left of numbers, not on the right. So we start with $6, and then we have to incorporate some sort of rate. So this negative 2/3 here, negative 2 over 3, relates dollars to minutes. So we lose $2 every 3 minutes. Just like that, we've got our words. We're also going to talk about functions versus non-functions, linear versus nonlinear. So in order to be a function, every input has exactly one output. What this is saying, in a little bit simpler terms, is that the inputs matter more than anything else. The outputs don't matter as much. It's all about the inputs. We have to study these ones first. Once we study these, that's when we move on to the outputs, a lot like independent variables and dependent variables. This matters more than this because it controls. IB controls DV. For things to be linear or nonlinear, we have to have a constant rate of change slash slope when we're in a table. It has to be a straight line if it's a graph, and one perfectly straight line. And then the last one is no weird stuff in the equation. And what I mean by weird stuff, and I mean it's just a blanket statement. We can't have exponents on the variables. We can't have absolute value. We can't have square root symbols. Can't have any of other weird mathematical stuff. If you look at a calculator, you see these buttons right kind of in the middle, sine, cosine, and tangent. None of those. I can't write down everything that breaks it of being linear. It is just weird stuff. Things that you, right now in your life in 8th grade math, go, whoa, that's weird. Most likely is not a linear function. So let's kind of take a look at it. Is it a function? Well, to check if it's a function, we're going to use what is called the vertical line test. The vertical line test says that if I take a line that's perfectly vertical like this, make it a little bit darker color so it's easier to see. I guess red will work the best. And I take it and I kind of move it across the graph, I should be able to leave this red vertical line anywhere and only cross once. So it doesn't matter where I leave it. I can leave it here, I can leave it here, I can leave, whoops, grabbed the wrong thing, over here. Anywhere I want, and it should only intersect the graph once. So as we kind of go across, like we're scanning it, our red line only crosses our black graph line one point regardless of where we are. Because of that, it is a function. To see if it's linear or not, all we have to do is ask the question, is it a straight line? The answer is no, therefore it's not linear. Maybe we have a table. When we have a table, looking over here at the inputs. Right away we should notice that the inputs, right here and here, are the same. Which means if they're the same, their outputs have to be the same. Every input has exactly one output. The way you can check is if I were to ask you what number pairs with this number 1, there should be no doubt on what number you give me. Since there is doubt, it is not a function. The best part of it not being a function is it's automatically not linear. You have to have a function before you can be linear. So again, we're going to check. Are any numbers the same over here on the left? None of them are the same. It is automatically a function. It does not matter that these two outputs are the same, because our inputs were not the same. The outputs don't matter. Now we're going to check to see if it's linear. We're going to need to have a constant rate of change. So from here to here, we went down 1, down 1. From here we went up 1, down 1. These two fractions, whoops, that kind of looks like a 7. Are not the same, so it is not linear. Maybe have in coordinate points. The first thing I would do is rewrite this as a table. -2, 4. Find my next smallest x value. I notice that 2, 4, -2, 4, the repeating points. I don't need to write it twice. 1, 5, 5, 8, 7, 10. Again, are any of these the same number? They are not. Even if we had listed our duplicate point, notice that they're exactly the same. This is a function. Yes. We check for it being linear. From here to here is 1. From here to here is 3. So that's 1 over 3. From here to here, that's 3 and 4. 3/4 and 1/3 are not the same. It is not linear. Again, we're back onto a graph. We're going to check our vertical line test. At any point, do we have the line crossing more than once? The answer is no. This is a function. Is it one perfectly straight line? No, so it's not linear.